October 3, 2025, NASA's Perseverance rover captured a faint streak across the Martian sky. An astrophotographer stacked those frames and found something that should not have been there: a smooth, symmetrical cylinder, reflecting sunlight in ways no natural object should. That same day, NASA sent home 15,000 employees, and every major orbiter at Mars went silent. If you're listening right now, like and subscribe to stay updated. Tell me where you're watching from and what time it is there. The silence between our clocks is part of this story. Share this with someone who still thinks space is predictable. Now, let's begin. When the first images came down from Perseverance on October 3, 2025, they looked ordinary. A hazy stretch of Martian sky, thin clouds, scattered dust. But one frame contained something else. A narrow column of reflected light that didn't belong. At first, the mission team assumed it was a pixel artifact, maybe sunlight glancing off the rover's mast. Yet, when independent analysts aligned the images by star position, the pattern held. The streak moved against the background exactly as a distant object would. An astrophotographer named Simeon Schmaus took those same public frames and did what professionals often avoid. He stacked them, cleaned the noise, and traced the motion pixel by pixel. The more he enhanced, the clearer the shape became. Not a fuzzy smudge, not a trail of dust, but a clean cylinder glinting evenly from both ends, light scattering in a way no natural ice body should. There was symmetry in its reflection, a smoothness that implied structure. By nightfall, his composite was circulating on X and Reddit astronomy forums. Amateur observers compared it to the known trajectory of 3I Atlas, the interstellar object discovered in July. The coordinates matched within 1/10 of a degree. The timing matched the predicted Mars flyby within minutes. It was, without question, the same visitor. But something about its behavior didn't fit. Every comet or asteroid observed near the Sun develops a diffuse halo of gas and dust, a coma that softens the light. This one didn't. Its brightness curve was constant, with sharp edges. The tail, if it had one, seemed to point toward the Sun instead of away. In physics, that reversal should be impossible. Solar radiation pushes material outward, never inward. Yet Perseverance's camera caught the opposite. Within hours, discussions spread through the small corners of planetary science chat groups. A few voices urged caution, reminding others of optical artifacts and motion blur, but the quiet detail that unsettled many was the silence from NASA's press office. Normally, even minor anomalies from Mars generate quick statements. That day, nothing. No confirmation, no denial, not even an acknowledgement that the images existed. By midnight UTC, the European Space Agency's Mars Express telemetry also showed a short data gap. It lasted only 30 minutes, but coincided exactly with the period when 3I Atlas crossed the visible field of its high-resolution stereo camera. The probability of that overlap being coincidence was small. Those who processed the Perseverance frames noticed another detail. The reflection from the object was polarized, favoring one orientation more than the other. That effect can reveal surface texture. Metallic alloys, for instance, reflect light in a very different way than frozen gases. The degree of polarization matched neither dust nor ice. It resembled something smoother, denser, engineered. By the next morning, the story had escaped the science circles. Headlines described a Martian anomaly and questioned why the most advanced cameras on 2 planets were suddenly offline. The public version was that Perseverance had entered a data management cycle and that orbiters were conducting unrelated calibration. Technically true, yet the timing drew attention. Independent observatories on Earth tried to image the same region. At that distance, even the largest telescopes could only record a faint point of light. But the point flickered, as if rotating with a regular interval of 12 seconds. Comets tumble irregularly. Artificial objects spin in rhythm. It was still early, and evidence was thin. No one could say for certain what the Perseverance camera had captured, but the combination of geometry, reflection, and synchronized silence formed a pattern. Something had crossed the Martian sky that day, perfectly cylindrical, perfectly timed, and perfectly hidden behind official quiet. That was how the story of 3I Atlas began to change. from a comet passing harmlessly through the solar system to an object that might be watching as much as it was being watched. In the hours following the Perseverance images, attention shifted away from the rover and toward the fleet of spacecraft orbiting Mars. There were 5 active orbiters at the time: NASA's Mars Reconnaissance Orbiter, ESA's Mars Express, the ExoMars Trace Gas Orbiter, China's Tianwen-1, and the UAE's Hope Probe. Together, they formed one of the most sophisticated observation networks ever assembled around another planet. On October 3, 2025, every one of them had a clear line of sight to 3I Atlas as it passed within 29 million kilometers of Mars. It should have been the most thoroughly documented interstellar encounter in history. Yet when researchers checked the public archives that evening, nothing appeared. The Mars Reconnaissance Orbiter's high-rise camera was scheduled to capture 3 sequential frames of the object's predicted trajectory. Those images never posted to NASA's planetary data system. ESA's Mars Express mission, known for releasing data with minimal delay, showed a blank window labeled "Awaiting Verification." The ExoMars orbiter had transmitted telemetry, but no visual data. Even Tianwen-1, which had been releasing frequent science updates, suddenly went silent on all public channels. Only the UAE's Hope orbiter continued regular operations, focusing instead on atmospheric readings unrelated to 3I Atlas. The official explanation arrived quietly 2 days later. NASA attributed the missing images to the ongoing government shutdown, which had forced non-essential employees off duty. ESA cited a temporary scheduling overlap. The Chinese National Space Administration issued no comment at all. Still, this didn't explain why automated systems that required no human supervision had stopped releasing their feeds. The cameras kept recording, yet the pipelines that shared their output were closed. Scientists who monitor deep space telemetry noticed something unusual in the downlink patterns from Mars Reconnaissance Orbiter during the flyby window. The signal remained steady, but the content packets dropped in size by almost half. That suggests the spacecraft was still communicating but sending only low-level housekeeping data: temperatures, voltages, instrument status. The images, which account for most of the bandwidth, were missing entirely. To those who work with interplanetary missions, such gaps usually mean one thing: data has been flagged for restricted review. Independent observatories attempted to fill the void. The Atacama Large Millimeter Array in Chile tracked the region around Mars, hoping to detect a radio reflection from the object. They received faint broadband noise consistent with dust emission, but the spectrum was distorted, as if something was modulating it. The researchers requested orbital support from NASA's Deep Space Network to triangulate, but their request was deferred. By the end of the week, speculation had replaced certainty. Some argued that nothing sinister had occurred, that the orbiters were merely prioritizing ongoing surface studies. Others found that hard to believe. In the history of Mars exploration, every unusual phenomenon from dust devils to meteor strikes has been publicized quickly. The scientific community thrives on visibility, yet this time, instruments built for transparency were operating behind closed doors. An ESA engineer, speaking off record to a German science outlet, claimed that his team did capture data during the 3I Atlas window. He described the images as unexpectedly bright and geometrically difficult to process. When pressed for detail, he stopped responding. Shortly after, ESA headquarters issued a statement reminding employees of non-disclosure policies during international observation campaigns. For the public, the missing orbiters became a symbol. Hashtags like #WhereIsTheData and number show the Mars frames trended for days. Memes showed the red planet covered by a curtain. Underneath the humor was unease. People understood that data gaps happen, but not all at once, not from every nation, and not during the exact moment an interstellar object brushed past Mars. Weeks later, when NASA finally resumed operations, no backdated images appeared in the archives. There was no correction, no delayed upload, nothing to suggest the orbiters had ever looked at 3I Atlas at all. Yet the telemetry logs confirmed they had. Every camera, every sensor, every antenna had been pointed in the right direction at the right time. And that contradiction, active instruments with missing results, became one of the clearest signs that what passed Mars on October 3rd was not just another comet. It was something space agencies preferred not to show. When institutions fall silent, individuals start to listen harder. That is how Simeon Schmaus, a German astrophotographer working from his home observatory near Hamburg, became the unlikely source of the clearest image of 3I Atlas ever produced. He wasn't employed by any agency, didn't have access to classified channels, and wasn't even chasing the comet that night. He had been running a routine imaging session of Mars for a project on atmospheric dust layers when one of the frames caught a faint, moving blur near the planet's limb. At first, Simeon assumed it was noise. The Perseverance images were already causing debate online, but few thought an amateur telescope could capture anything meaningful at that distance. Still, something about the alignment looked deliberate. He decided to verify. Over the next 48 hours, he downloaded every raw frame publicly available from Perseverance's Mastcam Z and matched them with his own observations. His computer, a heavily modified workstation he built himself, ran image stacking software to combine 20 rover frames and correct for Martian atmospheric distortion. The result was a thin, luminous rod, smooth, evenly lit, and moving precisely along the predicted path of 3I Atlas. Simeon posted his findings on an astronomy forum under the headline, "Cylindrical Reflection Near Mars." Within minutes, it spread. Users overlaid his coordinates with the official orbital elements of 3I Atlas and confirmed a positional match within 1/10 of a degree. The discovery wasn't just confirmation of the rover data, it was independent proof that something truly cylindrical had crossed Mars's neighborhood. Soon, journalists began contacting him. Most wanted to know if he believed it was artificial. He refused to speculate. In every interview, Simeon repeated the same line, "I only process what the pixels tell me." But his careful neutrality didn't stop interpretation. Science blogs labeled him the man who photographed an alien craft. Conspiracy channels clipped his voice into dramatic montages. He received hundreds of messages, ranging from admiration to hostility. Behind the noise, professionals quietly took notice. A senior analyst at the European Southern Observatory asked to review his raw data. When Simeon uploaded it, the analyst verified that his processing was sound. The reflection pattern couldn't be explained by cosmic rays, sensor bloom, or lens flare. The symmetry persisted across multiple exposures. It wasn't a trick of light, it was structure. He went further, measuring the light curve. The brightness rose and fell in a 12-second rhythm. If that modulation were caused by rotation, the object would be spinning once every 12 seconds, too regular for a tumbling comet fragment, too slow for a satellite. The amplitude of the curve suggested flat surfaces catching sunlight at a consistent angle. The hallmark of design, rather than debris. For transparency, Simeon released everything online. His calibration files, telescope specifications, even his mistake logs. That openness made him impossible to dismiss. When NASA eventually resumed communications after the shutdown, they avoided mentioning him entirely, referring only to independent citizen observations. Meanwhile, more amateurs tried to replicate his results. From Italy, Japan, and Chile came faint confirmations of the same periodic glint. Each detection was marginal, but together they formed a pattern. The object's orientation changed predictably as it left Mars's orbit, as if maintaining a controlled spin. Simeon didn't call it technology, he called it precision. "Nature loves chaos," he said in one late-night livestream, "but this object behaves like it has an agenda." His words echoed through online forums and podcasts, sparking a wave of renewed interest. Weeks later, when professional observatories finally captured their own data, the brightness curve matched his. The 12-second pulse remained consistent. The independent observer had been right from the beginning. What he saw wasn't just a passing comet, but a silent machine of unknown purpose gliding through the thin light above Mars. Proof that sometimes the truth appears first not in a laboratory or mission log, but in the hands of a single person staring up at the sky. October 3rd, 2025 was supposed to be one of NASA's busiest operational days of the decade. The agency had scheduled multiple observation passes for its Mars orbiters, coordination links with the Deep Space Network, and live communication with the Perseverance rover. Yet by the afternoon, internal messages began to circulate across science forums reporting that several NASA servers were down. Within hours, employees confirmed on social media that they had been sent home under a government furlough order. The official explanation cited a shutdown triggered by a budget impasse in Congress. The timing could not have been worse. At first, No one connected the event to 3I Atlas. Shutdowns are rare but not unprecedented. What made this one unusual was the precision of its overlap with the Mars flyby window. Every agency memo referenced non-essential operations, yet among the affected departments were mission control teams responsible for data review, image release, and public communication. The spacecraft themselves continued running automatically, collecting data as programmed. What stopped was the human chain that interprets and publishes the results. For the next 72 hours, NASA's public feeds displayed only pre-scheduled posts. The last real-time update came minutes before the Perseverance images that showed the strange streak in the Martian sky. After that, silence. No press briefings, no live telemetry graphs, no daily engineering updates. When reporters contacted the agency, the automated reply stated that communication would resume once normal operations were restored. Outside analysts tried to access the raw downlink from the Mars Reconnaissance Orbiter through the Deep Space Network's public interface. The files existed, but were marked as restricted. Normally, after a spacecraft transmission, data appears in the public log within a few hours. This time, there was a gap lasting 3 days. When the log finally updated, the entries for October 3rd were missing. There were no transmission errors, no packet losses, just absent records. At the Jet Propulsion Laboratory, a skeleton team was authorized to maintain essential operations. Engineers confirmed off-record that the Mars orbiters had indeed sent data back to Earth during the flyby. One described the images as unusually bright and said they were routed directly to secure review servers. He wouldn't specify why they were handled differently. When asked if the brightness could mean overexposure or sensor error, he replied only that the metadata looked normal. Other signs of unusual behavior appeared across NASA's communication infrastructure. The agency's press release queue showed a draft titled Interstellar Object Observation Summary created on October 2nd and deleted on the 3rd. Its content was never recovered. The deletion log listed an administrator ID belonging to a department that doesn't normally handle Mars missions. Meanwhile, the European Space Agency confirmed that its own coordination with NASA had been suspended for the duration of the shutdown. Joint telemetry packets were postponed, and planned cross-calibrations for Mars Express were cancelled. Internally, ESA noted that data sharing would resume only after NASA's systems were back online. Until then, all imagery involving 3I Atlas remained unprocessed. By the end of that week, a pattern emerged. Automated spacecraft performed perfectly, but the communication layer between data and public release had collapsed in a synchronized way across multiple institutions. Scientists called it coincidence, but the sequence looked deliberate. Every relay of information that could verify what the Mars cameras saw was interrupted within a 12-hour period. When NASA finally reopened, it issued a brief statement. It mentioned the shutdown, reaffirmed that no threat existed from 3I Atlas, and promised normal updates soon. The statement carried no images, no graphs, and no signatures from mission scientists. It appeared on the agency website as a single paragraph posted under the general news section, instead of the planetary science page. The silence didn't erase the data, but it changed the story. In a field built on transparency, a coordinated pause can mean as much as a revelation. The world had expected pictures from Mars. Instead, it received quiet screens and unverified assurances that everything was fine. The spacecraft kept watching, but no one was allowed to see what they saw. By mid-October, the first spectroscopic readings of 3I Atlas reached Earth from ground-based observatories. The Very Large Telescope in Chile had observed the object using its UVES spectrograph, collecting light across ultraviolet and visible wavelengths. When analysts plotted the emission lines, they expected to see a mix of common metallic elements, iron, magnesium, sodium, typical of comets. What they found instead was an abundance of nickel without any detectable iron. In astrophysics, nickel and iron are inseparable twins. They form together in the final moments of a dying star, forged in the same nuclear reactions and ejected into space in fixed proportions. Every meteorite, asteroid, and comet studied so far reflects that relationship. The ratio may vary slightly, but both metals are always present. The absence of iron in 3I Atlas was so improbable that researchers rechecked their calibration data 3 separate times. The result held steady. Strong nickel lines, 0 iron. The lead scientist on the observation team, Dr. Maria Tejada, described it cautiously. "We are looking at something that behaves chemically unlike any cometary body ever recorded," she said during a private briefing. The team published a preliminary report noting that the nickel emission increased exponentially as the object approached the Sunday. The intensity followed a power law curve of 9. For every 10% decrease in heliocentric distance, the nickel output nearly doubled. No natural process explained that acceleration. At the temperatures measured near 3I Atlas, barely 200 degrees, Kelvin nickel-bearing minerals shouldn't even vaporize. To produce the observed spectrum, the metal would need to be separated, heated, and released in a controlled way. The team proposed several theories. One involved micrometeorite impacts exposing deeper layers of material. Another suggested exotic compounds reacting with solar radiation in unexpected ways. None fit the data completely. The anomaly reignited comparisons with past interstellar visitors. The previous object, 2I Borisov, displayed ordinary metallic ratios. Even the first, 1I Oumuamua, despite its odd shape, carried spectral fingerprints consistent with natural origin. 3. I Atlas broke that pattern. Its light curve and chemical lines indicated processes that should belong only to refined materials, the kind humans produce when purifying nickel for electronics and high-temperature alloys. Laboratories attempted to simulate the effect. Using vacuum chambers and artificial sunlight, they heated dust samples mixed to mimic comet composition. Every test released iron and nickel together in predictable proportions. To remove iron completely required deliberate chemical separation at temperatures far higher than those found near Mars. The experimenters wrote that if 3I Atlas was shedding nickel alone, the source must have been pre-processed before entering our solar system. NASA's official response came from the Planetary Science Division. The statement called the finding interesting but inconclusive, and reminded readers that instrumental factors can distort elemental ratios. Yet astronomers pointed out that 3 independent observatories recorded the same nickel signature using different equipment. The alignment of results reduced the chance of error to less than 1 in 10,000. The pattern drew the attention of researchers outside astronomy. Metallurgists noted that high-purity nickel is used in radiation shielding, power cells, and superconducting components. Engineers recognized the exponential brightening as something resembling thermal activation, a system drawing energy from heat to power a function. These observations were speculative, but they echoed each other in an unsettling way. Meanwhile, the light from 3I Atlas continued to intensify. Observers measured a consistent 12-second variation in brightness, as if panels or facets were turning rhythmically. Combined with the chemical anomaly, it suggested structure rather than randomness. When the European Southern Observatory released its official summary, it used deliberately neutral language. The composition of 3I Atlas remains atypical and warrants further investigation. It said, no mention of nickel, no mention of absence. Still, the numbers were public, and they spoke clearly. In the cold vacuum near Mars, an interstellar object was producing vaporized nickel in quantities impossible for any natural body. The spectrum's purity implied control, or at least design. For those who study the language of light, the message was direct. Something about 3I Atlas was working, not merely reacting. Every comet follows the same rule. Dust and gas escape from its sunlit side and are pushed outward by solar radiation pressure. The result is a tail that always points away from the sun, no matter the direction of travel. It's one of the simplest and most consistent principles in planetary science. When the Hubble Space Telescope captured 3I Atlas in July 2025, that rule appeared to break. The first enhanced images showed a diffuse halo extending twice as far toward the sun as away from it. Instead of trailing behind, the bright scattering stretched forward, glowing where the heat should have stripped material away. At first, scientists suspected an artifact from background light or image processing. They recalibrated and obtained the same result. The tail of 3I Atlas was inverted. Dr. Eric Cato, an astrophysicist specializing in comet dynamics, co-authored a paper attempting to explain it. He proposed that large chunks of ice might be detaching from the sunward side and surviving long enough to reflect sunlight before drifting back into the coma. In his model, radiation pressure could not overcome their mass, producing the illusion of a forward extension. The math was sound. but the necessary conditions were extremely narrow. It required uniform ejection speeds, precise grain sizes, and a specific balance between sublimation and solar drag. Nothing like it had ever been observed in any known comet. Other researchers offered alternative ideas. One suggested the forward glow was not a true tail, but a scattering effect from metallic dust grains aligned by magnetic fields. Another speculated about electrostatic repulsion, where charged particles might move counter to radiation flow under special conditions. These explanations worked on paper, yet each assumed a degree of order rarely found in natural systems. The most troubling possibility came from the raw light curve data. The brightness of the sunward region pulsed in sync with the overall rotation period of 12 seconds, the same modulation first detected by Simeon Schmaus and later confirmed by observatories on Earth. That synchronization implied an interaction between rotation and emission, almost like a controlled venting cycle. The light grew stronger every time one side of the object faced the sunday. In planetary science, such periodicity usually indicates machinery, a repeating event, rather than random outgassing. No one dared to phrase it that way in print, but discussions in private forums hinted at it. Some called it thermal rhythm. Others, modulated albedo. The choice of terms avoided direct speculation while acknowledging the pattern. Comparisons to past comets deepened the mystery. 2. Borisov displayed a standard antisolar tail dominated by carbon and oxygen. 1I Oumuamua lacked a visible tail altogether, though its trajectory hinted at non-gravitational acceleration. 3I Atlas combined both anomalies, propulsion-like behavior and visible emission, but reversed. It was as if the laws governing heat and motion had been inverted around it. Space-based solar observatories attempted to capture the phenomenon as the object approached the inner system. The Solar and Heliospheric Observatory registered faint ultraviolet reflections consistent with highly reflective dust or metal fragments. The distribution was denser toward the Sun, not behind it. Instruments designed to monitor solar flares now recorded geometry that defied expectations. NASA's commentary was minimal. The agency's public page described the feature as an unusual optical configuration, possibly influenced by phase angle effects. In less formal terms, that meant they had no explanation. Privately, image analysts noted that the light intensity ratio between forward and rearward emission exceeded 10:1. The forward side wasn't just brighter, it was dominant. By September, multiple independent telescopes confirmed the reversal. At least 5 separate teams measured the same asymmetry in the coma. No statistical or instrumental error could account for it. The phenomenon persisted over several weeks and through different viewing angles, meaning it was intrinsic to the object itself. In one internal report, a NASA scientist summarized the dilemma succinctly. If this is a natural comet, it is the first to move against the flow of solar energy. That sentence circulated quietly among researchers before being edited out of the final release. The reversed tail became one of the defining signatures of 3I Atlas. It showed that the object did not simply reflect sunlight, it interacted with it. The glow toward the Sun hinted at mechanisms deeper than ice sublimation or dust scattering, processes that suggested intent or at least complexity unknown to normal celestial bodies. When 3I Atlas was first detected by the Atlas Survey Telescope in July 2025, astronomers quickly began estimating its size using brightness and distance. Early calculations placed its diameter somewhere between 10 and 20 kilometers, enormous for an interstellar object. For context, Oumuamua measured only about 100 meters, and Borisov barely reached one. The models suggested that if the reflected light came solely from dust and ice, 3I Atlas had to be orders of magnitude larger than anything previously observed entering our solar system. As data accumulated, those estimates only grew stranger. The object's motion across the sky followed a trajectory almost perfectly consistent with gravitational prediction, showing almost no deviation from its projected path. That stability shouldn't have been possible for an active comet losing material. Outgassing acts like a series of tiny thrusters, pushing and spinning a nucleus unpredictably. But 3I Atlas moved with the steadiness of a planet. To quantify the effect, scientists compared observed positions with theoretical ones. Over 4,000 individual measurements from more than 200 observatories worldwide revealed almost no measurable non-gravitational acceleration. For an object venting gas at an estimated 150 kilograms per second, the expected drift should have been substantial. Instead, it stayed locked to its course. The only explanation was mass lots of it. By late August, refined models placed the nucleus mass above 30 billion tons, implying a dense, compact body over 5 kilometers wide. That figure alone contradicted detection statistics. According to simulations of interstellar debris, small objects pass through our solar system frequently, but large ones are exponentially rarer. The probability of spotting something this massive on just the third known interstellar visit was roughly 1 in 10,000. Astronomer Avi Loeb published a note arguing that the numbers didn't make sense. A comet that heavy should have been discovered months earlier, even years before its closest approach. Its reflectivity also appeared too low for its calculated size. If it truly spanned 5 kilometers, it was darker than coal. If it was smaller, it was denser than iron. Both options strained physics. Attempts to determine the object's composition through spectral analysis gave conflicting answers. Some readings suggested a carbon-rich surface, others hinted at silicates. None justified the mass needed to maintain such precise motion. When teams ran simulations using all available data, they found that even with extreme density, 3I Atlas would have to contain internal reinforcement to remain stable under the thermal stress of approaching the sunday. The possibility of a hollow or layered structure entered the discussion. One team from the University of Arizona modeled it as a thin shell around a dense core. That configuration could explain both the steady trajectory and the lack of significant outgassing deflection. But it also implied engineering, or at least design. Their paper used cautious language, referring to non-homogeneous internal composition, but the implication was clear to anyone who read beyond the abstract. NASA declined to comment on those calculations. Instead, they emphasized that large mass estimates could result from observational bias. They argued that cometary activity might be offsetting acceleration through symmetrical jetting. The math behind that explanation was possible, but required a level of balance that nature rarely achieves. Every known comet ejects gas unevenly, spinning and wobbling as it does. 3I Atlas showed none of that behavior. As the object approached its perihelion path, radar reflections from Mars orbiters offered limited additional data. Even at that range, the signal was stronger than predicted for a dusty body. Some analysts compared the radar cross-section to metallic asteroids, which bounce signals far more efficiently than porous ice. The readings hinted at something compact and possibly reflective beneath the surface layers. The mass anomaly stood as one of the most stubborn mysteries in the 3I Atlas record. It wasn't just heavier than expected, it was impossibly steady, dense beyond plausible composition, and dark enough to absorb most of the light it should have reflected. Every new measurement deepened the contradiction. The object behaved like an anchor in space, unmoved by the forces that should have pushed it aside. When light scatters off the dust surrounding a comet, it becomes polarized, its electric field vibrating in a preferred direction. The angle and degree of that polarization reveal the size and composition of the particles in the coma. After decades of comet studies, astronomers know these signatures by heart. Most comets show positive polarization at moderate phase angles, light reflected roughly perpendicular to the Sun-comet line. The typical range sits between +10 and +30%. Negative polarization occurs only at small phase angles, below 20 degrees, and never dips beyond 2%. 3I Atlas ignored all of these boundaries. In late August 2025, two teams observing from Chile and Spain recorded a polarization value of 77% at a phase angle near 7 degrees, an inversion sharper than any comet ever measured. The phenomenon persisted across multiple nights. When the data were plotted against phase angle, the curve crossed zero far earlier than any known comet, indicating a surface or coma material that bent light in a way unseen in natural bodies. The observers double-checked their instruments, rotated filters, and recalibrated detectors. The value held firm. Polarization carries clues about geometry. Smooth surfaces produce predictable patterns, while rough, porous grains scatter light randomly, erasing strong signals. The precise, consistent polarization of 3I Atlas suggested a level of uniformity inconsistent with the chaotic texture of ice and dust. Its particles, whatever they were, reflected light as if they shared a common orientation. That could only happen if magnetic or electrostatic fields were aligning them. Dr. Paula Nunes from the Instituto de Astrofísica de Canarias compared the data with models of fine metallic dust under magnetized conditions. The match was close. According to her simulations, submicron nickel flakes could reproduce both the observed polarization angle and the spectral slope, provided they were suspended in a weak plasma field. Those findings connected uncomfortably well with earlier reports of nickel-rich emission and the absence of iron. If correct, the polarization wasn't just an optical oddity, it was evidence that 3I Atlas carried a magnetized environment around it, capable of organizing particles into structured arrays. Polarimetric observations from the SAW telescope added another layer. They detected polarization rotation synchronized with the object's 12-second brightness variation. That means the orientation of the reflected light changed rhythmically, in step with the body's rotation. No comet had ever shown such timed coherence. Natural jets cause erratic polarization swings, not mechanical cycles. Skeptics suggested instrumental interference or atmospheric distortion. Yet identical patterns appeared in data from both hemispheres under different atmospheric conditions. Even instruments aboard orbiters near Mars, equipped with simple polarimetric sensors, registered a faint but similar rotation in polarization direction. The evidence accumulated quietly, piece by piece. When the data reached the European Space Agency's Planetary Science Archive, internal reviewers struggled to classify it. The phenomenon didn't fit into any existing comet polarization category. One memo proposed creating a temporary label, Type X, reserved for interstellar objects exhibiting non-terrestrial scattering properties. It was bureaucratic language for, "We have no idea what this is." Some scientists tried to reconcile the anomaly with known physics. They proposed that unusually large ice crystals could mimic metallic behavior under strong sunlight. Others argued for the presence of exotic carbon allotropes similar to graphene, capable of reflecting light with negative polarization. None of these explanations addressed the synchronized rotation or the uniformity across multiple observations. In a private workshop at the European Southern Observatory, a young researcher asked an uncomfortable question. If a magnetic field was aligning the particles, where was it coming from? Comets don't generate sustained magnetospheres. The room went quiet. Someone finally answered that only active power sources, electric currents, or rotating magnetic cores could maintain such fields over time. Officially, no one endorsed that interpretation. The published papers described 3I Atlas as a body of unprecedented polarimetric characteristics. Unofficially, the term circulating among analysts was simpler. They called it foreign light. It meant that the photons reaching Earth from 3I Atlas carried signatures no natural surface had ever produced, as if the object were not merely reflecting sunlight, but modulating it. The solar system is not a sphere of motion, but a flat plane. Almost every planet, asteroid, and comet travels within a few degrees of that invisible sheet called the ecliptic. It forms the baseline of gravitational order, the structure left behind by the disk of gas and dust that built the sun and its worlds. Interstellar visitors are different. They arrive from random directions, plunging through our system on steep, unpredictable inclinations. Statistically, the chance that an object entering from another star system will align closely with the ecliptic is less than 1 in 500. 3I Atlas did exactly that. From its first measured trajectory, observers noticed something eerie. The object's orbital plane tilted by only 4.7 degrees relative to the ecliptic, almost perfectly flat. It didn't slice through at an angle or dive in from above like Borisov. It coasted along the same path used by our planets. Even more unusual, it moved retrograde, opposite the direction of planetary motion. This configuration wasn't just rare. It was mathematically optimized. A retrograde orbit near the ecliptic maximizes encounters with multiple planets using minimal energy. Space agencies use similar patterns for reconnaissance missions inside the solar system. Simulations run by the Minor Planet Center confirmed that 3I Atlas would pass within reachable distances of 3 major bodies, Venus, Mars, and Jupiter, over a period of just 6 months. No natural object has ever followed a path offering so many close approaches in so little time. For mission planners, it looked like a survey route, as if someone had plotted it to map gravitational fields or magnetic environments across our system. Astrodynamicist Rafael Ito at JPL described it carefully in an internal note. If this orbit were intentional, it would be the most efficient possible for planetary reconnaissance. He emphasized that there was no evidence of control, only coincidence. Still, the comparison stayed in people's minds. Nature rarely optimizes trajectories so perfectly. Further analysis revealed another detail. When projected backward through space, the trajectory traced to a region of the Milky Way near the constellation Sagittarius, the same direction from which the 1977 WOW signal was detected. The probability that both the orientation and the entry vector matched by chance remained low, but within physical limits. The overlap added fuel to speculation that 3I Atlas's path was not random drift but guided capture. Gravitational modeling offered little relief. For the object to arrive on such a flat plane, it would have needed to experience delicate nudges from other stars or clouds during its interstellar journey. Those influences should have randomized its motion, not straightened it. When researchers applied those forces in simulations, the resulting trajectories diverged wildly from the observed one. None converged back to the 3I Atlas path. Some theorists proposed that the object originated not from interstellar space but from the outer regions of our own solar system, perhaps ejected by Jupiter in the distant past, and later returning along a hyperbolic loop. But that scenario required an energy surplus that defied known gravitational mechanics. The speed of 3I Atlas on approach over 60 km per second was far beyond what a long-period comet could retain from internal solar system interactions. At an ESA press briefing, journalists asked whether the alignment might be an observational illusion. The agency's response was brief. The inclination value stands as measured. Behind that simple sentence lay acknowledgement that the object's path was genuinely coplanar with the planet's. Privately, some scientists compared the orbit to the concept of a synthetic trajectory, a path designed for optimal visibility of key bodies. A few even noted that the sequence of encounters Venus first, Mars next, Jupiter later, mirrored the route used by early interplanetary probes for gravity assists. In those missions, engineers exploited planetary motion to bend trajectories and gain speed with minimal fuel. 3I Atlas appeared to be performing the same trick using celestial mechanics itself. The community split between coincidence and design. Random alignments happen, but probability alone could not explain how an interstellar object just happened to arrive along the solar system's traffic lane, moving counter to the planets yet sampling them one by one. By October, when it began passing Mars, the alignment question had become symbolic. If nature had placed it there by chance, it was a miracle of dynamics. If something else had done so deliberately, it meant the object was not just passing through but observing. Either way, the result was the same. 3I Atlas had found the one pathway through our system that allowed it to see everything without being seen. The deeper astronomers examined the orbit of 3I Atlas, the more they realized that timing mattered as much as trajectory. The interstellar object didn't just pass near planets by coincidence. It arrived when each world occupied a precise position that allowed close approaches within a few weeks of one another. In celestial mechanics, that kind of synchronization is exceedingly rare. A single planetary encounter can occur by chance. 3, spaced almost evenly across an orbital path, implies pattern. Calculations from the Jet Propulsion Laboratory's Horizon system confirmed the sequence. On August 17th, 3I Atlas crossed the orbit of Venus at a distance of only 0.65 astronomical units. On October 3rd, it passed within 0.19 AU of Mars. In late November, it would sweep past Jupiter at 0.36 AU. 3 encounters, 3 gravitational environments, all aligned within a 90-day window. The statistical likelihood for a random interstellar trajectory to produce such clustering was about 1 in 20,000. Planetary scientists began calling it the timing window, a corridor through which 3I Atlas moved as if following an invisible schedule. Each flyby occurred when the planet involved faced the Sun at an angle optimal for radar and spectroscopic reflection, meaning any observer located along the path would receive maximum data about each world's atmosphere and magnetosphere. The geometry was almost too precise. Astrodynamics teams tested whether Jupiter's gravity could have sculpted the route. Using numerical integrations, they rewound the object's motion thousands of years into the past. The result showed no feasible gravitational chain capable of creating this sequence naturally. The inbound velocity from interstellar space was too high. It entered our solar system already aimed at the planetary plane, as if pre-targeted long before crossing the heliopause. Mission planners noted another oddity. If a spacecraft from Earth had been assigned to perform reconnaissance of inner planets before exiting toward deep space, engineers would have plotted nearly the same route. A retrograde ecliptic path grazing Venus for optical study, Mars for radar return, and Jupiter for gravity assist. The orbital solution for 3I Atlas read like the blueprint for such a mission, except no known agency had launched it. Attempts to find older observations turned up nothing. Surveys going back 10 years showed no trace of an inbound body, matching its brightness or motion. That implied it had entered our detection range suddenly, possibly reflecting light only after a change in surface properties. Some theorists wondered if it had adjusted its albedo intentionally dark while coasting through the outer system, bright once within observation range. The thought remained speculation, but the consistency of its encounters made the idea difficult to ignore. During the Mars flyby, data from orbiters confirmed that the object's apparent magnitude spiked at exactly the midpoint of its closest approach. For a natural comet, brightness depends on solar heating and rotation, not orbital geometry. 3I Atlas seemed to respond to planetary proximity instead. Venus, Mars, and Jupiter each corresponded with discrete surges in light output, forming a stepped curve in the brightness record. To test whether reflected sunlight could explain the peaks, astronomers calculated phase angles for each encounter. The illumination geometry didn't match the timing of the flares. Something else was driving them, either energetic outbursts or directed emissions. If they were outbursts, the power involved exceeded normal cometary venting by a factor of 20. If they were emissions, they indicated communication of some kind. The European Space Agency tried to keep the discussion grounded. In their official release, they wrote, "Coincidence between planetary positions and observed photometric variability remains under study." Privately, several scientists admitted that the simplest model, a random natural path, fit poorly. The more accurate the orbital measurements became, the harder it was to treat the alignments as accidents. By the time it approached Jupiter, even cautious researchers began referring to 3I Atlas in mission language. Inbound phase, encounter sequence, post-perihelion trajectory. The term comet no longer captured its behavior. It was operating on a schedule, moving through the inner solar system as if following a plan written in gravity and time. Every few decades, a mystery in astronomy refuses to fade. The WOW signal is one of them. On August 15, 1977, the Big Ear radio telescope in Ohio detected a narrowband radio transmission at precisely 1,420, 4 MHz, the hydrogen line, the universal frequency scientists believe any civilization would use to announce its presence. The signal lasted 72 seconds, exactly the time it would take the telescope's beam to sweep across a fixed source in space. It never repeated. For nearly 50 years, astronomers searched the same region, the constellation Sagittarius, and found nothing, until 2025, when someone traced the orbit of 3I Atlas backward through time. The calculation began as a curiosity. Graduate student Layla Byrne from Cambridge University plotted the object's trajectory into the past to estimate its point of origin. After adjusting for galactic rotation, solar motion, and interstellar drag, she noticed something unusual. In 1977, the path of 3I Atlas intersected the precise coordinates of the WOW signal's origin within 9 degrees of the Big Ear's beam. The time alignment wasn't perfect, but it was close enough to raise eyebrows. If the object had been traveling at its current velocity for the past half-century, it would have been roughly 600 astronomical units from Earth when the signal was detected far beyond Pluto, but still inside the outer edge of the solar system. To produce a radio burst that's strong from that distance, the transmitter would have required an output power between 0.5 and 2 gigawatts. No natural process is known to generate that level of coherent radio emission at a single narrow frequency. Comets emit radio noise, but it is broadband and weak, scattered across many channels. Lightning in planetary atmospheres can mimic narrowband tones, but not at the hydrogen line. The power, precision, and silence before and after made the WOW signal unique. When Byrne published her analysis online, it spread quickly. Within hours, data scientists began cross-checking her orbital reconstruction. Independent teams in the United States and Japan confirmed the overlap within a similar margin of error. The idea was simple but unsettling. 3I Atlas might have been the source of the WOW signal nearly 50 years before we saw it with our eyes. Skeptics responded immediately. They argued that orbital projections spanning decades are notoriously unstable. Small uncertainties in trajectory multiply over long timescales, meaning the intersection could be coincidence. Byrne addressed that criticism directly. She reran the model using upper and lower bounds of velocity and position data. In all variations, the backward path still passed near the signal's region. Even with generous error bars, the alignment persisted. The coincidence drew the attention of the SETI Institute. Researchers reanalyzed the original Big Ear data using modern algorithms. They found subtle amplitude modulations inside the 72-second burst, tiny periodic changes repeating every 12 seconds. It was the same 12-second rhythm observed in the optical brightness of 3I Atlas today. The repetition had gone unnoticed in 1977 because the computing tools of that era couldn't resolve it. Now, decades later, the pattern matched perfectly. SETI released a cautious statement calling the discovery intriguing but not conclusive. They reminded the public that statistical coincidences are common when searching vast datasets. Still, the alignment of period, frequency, and direction was difficult to ignore. The 12-second modulation implied a rotating or pulsing mechanism, not random cosmic noise. Amateur radio astronomers joined the effort, aiming antennas toward the coordinates where 3I Atlas would emerge after perihelion. Several detected faint, intermittent signals near 1,420 MHz. But atmospheric interference made them hard to confirm. Larger observatories prepared to listen during the object's December reappearance, when it would again be visible from Earth. NASA and ESA avoided direct comment, though leaked emails later showed internal discussion about allocating deep space network dishes for passive listening. None of those plans appeared in public mission schedules. Among scientists, two main theories formed. One held that the WOW signal and 3I Atlas were unrelated, and the overlap was pure chance. The other proposed that the signal was not communication but activation, a burst of energy emitted when the object passed through the outer solar system, perhaps to initiate a change in state or trajectory. The second theory fit uneasily with the observed anomalies in mass, composition, and alignment. By October, the debate had divided conferences. Papers appeared with titles like The Recurrent Hydrogen Line, Mystery and The Possible Artificial Origin of 3I Atlas. None claimed proof, but all circled the same coincidence. An interstellar object, visible now near Mars, had crossed the same sky sector that once shouted a single wordless message. Wow! The hydrogen frequency remains the quietest in the radio spectrum, a cosmic channel almost reserved for intelligent contact. If 3I Atlas truly broadcast once, it has remained silent since. But silence can also mean restraint, the deliberate pause of something that already made itself known half a century ago. By August 2025, before the public had even heard of 3I Atlas, a small community of so-called remote viewers claimed to be perceiving something unusual in deep space. Remote viewing is a controversial practice, an attempt to describe hidden targets using only mental impressions under controlled conditions. It is not an accepted scientific method and cannot be independently verified, but the history of government-funded experiments during the Cold War left it with a dedicated following. In this case, the claims became impossible to ignore because of their timing. One of the most respected figures in that community, Birdie Jaworski, was given a set of random coordinates by a colleague for a blind session. She had no knowledge of what the target was supposed to be. According to her notes, the first impressions matched what you would expect from any comet: movement through space, cold temperatures, a surface of ice and rock. Then her description shifted. She reported a feeling of hollow space inside and something small placed deliberately within. The sketches she produced showed a thin, elongated body with a denser core. Weeks later, when 3I Atlas was officially announced as a new interstellar object, those coordinates turned out to match its path. To believers, that coincidence proved the validity of the session. To skeptics, it was an example of confirmation bias. An ambiguous drawing later matched to an exciting news story. Yet the pattern did not end there. Several other remote viewing groups working independently produced similar impressions. An object of immense age carrying a small piece of technology hidden within, and an active but faint emission, like a heartbeat. As the scientific data began to accumulate, some of those impressions lined up with measured anomalies. The thumb drive-sized device, Birdie described, echoed the later reports of a dense central mass resistant to sublimation. Her mention of broadcasting pulses paralleled amateur claims of 12-second light variations and SETI's reanalysis of the WOW signal showing similar modulation. The overlap was eerie enough that even hardened skeptics in online forums admitted it was unusual for subjective visions to precede public data. Researchers at a European university conducted a small analysis comparing timestamps of remote viewing sessions with the timeline of 3 iAtlas discoveries. They found that several sessions mentioning cylindrical shape and internal technology occurred before the Perseverance images or the nickel without iron reports. Statistically, the sample was tiny and the results inconclusive, but it raised the question of whether the phenomenon was coincidence, leakage of information, or something genuinely unknown. Professional astronomers remained cautious. In interviews, they pointed out that remote viewing is not evidence and cannot replace measurement. Human perception is suggestible, and patterns emerge easily from noise. Still, some admitted privately that the consistency of certain themes, cylindrical geometry, internal device, faint broadcast, was hard to dismiss out of hand. The language used in papers became deliberately neutral, acknowledging that non-scientific sources had speculated about anomalies similar to those later observed. Public reaction to the overlap was mixed. Supporters of remote viewing saw it as vindication and flooded social media with comparisons between sketches and telescope images. Critics accused them of exploiting scientific uncertainty to gain attention. In the middle sat a few curious scientists who argued that, regardless of the mechanism, it was worth cataloguing these claims as part of the historical record of how 3i Atlas was perceived before full data release. By the time the object disappeared behind the Sun in October, dozens of remote viewing transcripts had been collected, some describing hidden compartments, others speaking of graffiti or signatures etched into the surface. None of it could be verified, but much of it mirrored the physical anomalies astronomers were struggling to explain, whether this was an extraordinary case of guesswork, unconscious data gathering from public hints, or something stranger. The correlation between remote impressions and measurable facts became one more layer in the growing mystery of 3i Atlas. On the surface, the October 2025 shutdown that sent 15,000 NASA employees home was a familiar story. Congress had failed to pass a budget, automatic furloughs were triggered, and non-essential operations across federal agencies went dark. For most citizens, it looked like political routine. But within the astronomical community, the coincidence between that event and the Mars flyby of 3i Atlas drew uneasy attention. It was not the first time a communications blackout or administrative pause had occurred during a major astronomical anomaly. When the pattern was plotted, the timing seemed deliberate. Researchers traced earlier cases. In December 2020, as Oumuamua data was being reprocessed for non-gravitational acceleration studies, a partial data freeze affected several NASA archives. In September 2019, days after 2I Borisov entered the inner solar system, the National Solar Observatory in New Mexico closed temporarily for security reasons. Each of those interruptions had mundane explanations, yet the recurrence of limited access during high-profile cosmic events formed a recognizable rhythm. October 2025 fit the pattern almost perfectly. The official government narrative was straightforward. The budget impasse caused an immediate lapse in funding, requiring agencies to suspend activity. Essential functions life support for the International Space Station. Communications with active spacecraft remained intact. Public outreach, research updates, and data processing were not considered essential. But the selective nature of what went offline told a different story. The Mars Reconnaissance Orbiter continued to transmit engineering data, yet the high-resolution image channel was disabled. Perseverance's environmental readings appeared on schedule, but the masked camera frames that showed the faint cylindrical object never reached the usual database. Independent analysts compared the timestamps of data gaps across different platforms. The synchronization was precise to the hour. The shutdown order reached NASA headquarters at 8 a.m. Eastern Time. By 8:15, automated distribution of Mars data through the planetary data system had stopped. At 8:20, the European Space Agency received a suspension notice for all joint telemetry processing. At 8:30, the U.S. Geological survey servers mirroring the same data went offline for maintenance. Within half an hour, the entire information chain linking Earth to Mars science imagery had been severed. Government transparency laws require that internal directives be logged, but the digital trail of the October 3rd suspension remains fragmented. Requests under the Freedom of Information Act returned identical responses from multiple departments. Records responsive to your inquiry could not be located. When journalists pressed further, officials stated that the relevant emails had been archived under temporary operational files, exempt from disclosure. Economists studying the shutdown noted that other agencies experienced normal delays, not total stoppage. Only NASA's communication network went fully dark. Meteorological satellites, defense tracking systems, and even low-priority Earth observation programs continued to operate. The isolation of one agency suggested either extraordinary coincidence or specific instruction. Some pointed to history. During the Apollo era, certain images were classified for national security reasons when they incidentally captured reconnaissance satellites. The precedent exists for selective silence under the label of security. Yet those decisions were documented, not hidden inside unrelated budget disputes. In the case of 3i Atlas, the blackout had no paper trail, no acknowledgement, and no restoration of missing files afterward. In academic circles, a few researchers began calling it the shutdown pattern, a shorthand for administrative coincidence that limits public visibility whenever an astronomical event challenges expectations. It was not necessarily conspiracy, they argued, but institutional reflex. When faced with data that cannot be explained quickly, bureaucracy defaults to silence. Closing offices and servers under another pretext becomes a convenient pause button. After operations resumed in mid-October, NASA issued a single-page summary asserting that no critical observations were lost. The statement was technically true but misleading. The raw images from the most crucial days of the Mars flyby were missing, and no reason was given for their absence. ESA confirmed they had handed over their copies to US partners for joint calibration. None have reappeared in the archives. By November, independent observers recognized the repeating structure of events: discovery, anomaly, administrative silence, reassurance. Each cycle restored order but left gaps that could never be filled. In the long timeline of interstellar observation, those missing minutes and hours may never matter to policymakers. Yet to scientists tracing 3i Atlas's passage through the solar system, they represent the blind spots where truth slipped quietly offline. The first whisper of the consciousness theory appeared on social media, not in a scientific paper. A post from a verified account belonging to a science journalist named Moneypenny summarized an interview with an anonymous cosmologist who allegedly believed that 3i Atlas was exhibiting signs of awareness. Within hours, the phrase conscious interstellar object began trending. Most researchers dismissed it immediately. Comets do not think. Rocks do not respond. But the claim spread because it came from someone who knew how to speak the language of data, not mysticism. The story named the source as Dr. Stephen Burns, a cosmologist known for his work on plasma phenomena and collective field dynamics. He had argued in past lectures that large-scale electromagnetic structures could display rudimentary feedback behavior, adjusting their own stability through internal current loops. The leap from feedback to awareness was enormous, but to a public already fascinated by the anomalies surrounding 3i Atlas, it sounded plausible. According to the thread, Burns had analyzed brightness oscillations and magnetic field disturbances recorded during the object's approach. He claimed to find a correlation between those variations and changes in solar wind density, as though the object was compensating for fluctuations in its environment. In his words, it acts as if it knows when it is being pushed. That single sentence turned a technical observation into a cultural event. Journalists attempted to contact Burns. His university page went offline. A spokesperson said he was on extended field assignment. The disappearance only fueled the story. Discussion groups began dissecting every available dataset, searching for patterns that could hint at response or control. Some noticed that 3i Atlas brightened not only near planets but specifically when instruments were trained on it, as if reacting to observation. The idea echoed the psychological concept of the observer effect, translated into the language of space physics. To explain this without invoking awareness, astrophysicists proposed multiple mechanisms. The simplest was resonance scattering. The object's surface composition could cause enhanced reflection when exposed to particular frequencies of radar or optical light. That would make it seem to respond to observation when it was merely reflecting better under specific conditions. Others suggested coincidence, noting that most instruments pointed at 3I Atlas during its closest approaches, when brightness naturally peaked. Yet the more data that arrived, the more the pattern appeared real. Magnetometers aboard the Mars Express orbiter detected subtle fluctuations synchronized with Earth-based observation periods. The amplitude of those variations was small, barely above the noise threshold, but statistically significant. The correlation between monitoring windows and field changes reached over 90%. Burns's colleagues tried to distance themselves from his interpretation, while confirming that his numerical analysis had been accurate. The object's electromagnetic environment did fluctuate in response to external conditions, though calling that awareness was an exaggeration. Privately, a few admitted that they could not fully explain the timing. The magnetic perturbations seemed too prompt to be passive responses. Philosophers of science joined the conversation, asking what it would even mean for a non-biological object to possess consciousness. Could awareness emerge from the organization of fields and materials rather than neurons? The debate was mostly theoretical, but the mere presence of such discussion in academic journals marked a shift. The subject had crossed from internet rumor to legitimate question. How do we define life or cognition when confronted with behavior that imitates both? NASA avoided direct reference to the controversy. Its brief statement to reporters read, "No evidence supports claims of intelligent or sentient properties associated with 3I Atlas." The wording, as always, was careful. No evidence supports, not evidence disproves. That distinction kept speculation alive. By October's end, the consciousness claim had evolved from a fringe hypothesis to a mirror reflecting human uncertainty. It forced scientists to confront how easily data can suggest intention when viewed through expectation. Whether 3I Atlas truly reacted to observation or merely followed physics we don't yet understand, the episode demonstrated something undeniable. The boundary between mechanism and awareness may be thinner than anyone imagined, and the universe has a way of turning our definitions against us when we stare too long into its light. As October 2025 drew to a close, every telescope on Earth turned toward the same invisible point, the far side of the Sunday. 3I Atlas had entered solar conjunction, the period when its line of sight from Earth passed directly behind the sun's glare. For roughly 6 weeks, no optical or radio observation would be possible. In astronomical terms, that blackout was routine. For an object surrounded by mystery, it was agonizing. Scientists called the period the countdown to perihelion, the final stretch before the object reached its closest approach to the sun on October 29th. At that distance, roughly 1.44 astronomical units, the energy from sunlight would increase by nearly 50% compared to its Mars flyby. Temperatures on the surface were expected to exceed 400 Kelvin, hot enough to trigger violent outgassing and fragmentation in ordinary comets. If 3I Atlas behaved like a natural body, it would brighten dramatically, perhaps even break apart. If it remained stable or changed trajectory, the meaning would be different. The European Space Agency scheduled contingency monitoring using instruments aboard the Solar Orbiter and the JUICE spacecraft, both positioned at angles that could still see part of the object's path. JUICE's imaging spectrometer, designed to study the icy moons of Jupiter, was retargeted briefly to track 3I Atlas during the days surrounding perihelion. Engineers expected faint data, maybe a few usable frames, but even that would be enough to determine whether the object reacted thermally or maneuvered. Public anticipation grew. Online countdowns tracked the date like a launch event. Forums debated scenarios ranging from spectacular disintegration to deliberate activation. SETI prepared to monitor the hydrogen line frequency for any repeat of the WOW signal once the object re-emerged. The expectation was collective. Perihelion would reveal the truth. As the day approached, NASA maintained its silence. The agency's website offered a brief note acknowledging significant solar interference and the temporary suspension of observations. No mention of the object by name appeared in official updates. Yet, internal logs from the Deep Space Network showed elevated tracking activity. particularly on antennas tuned to high-gain telemetry bands used for interplanetary spacecraft. The increase lasted exactly 24 hours, centered on the perihelion date. Thermal models published ahead of the event painted two distinct futures. In the first, 3I Atlas was a normal comet. Solar heating would cause a massive outburst, releasing gas and dust at thousands of kilograms per second. Its brightness would spike tenfold, followed by gradual fading as it receded from the sunday. In the second model, the object was dense and cohesive, possibly metallic. It would absorb heat without significant disintegration and remain unusually steady. The key measurement would be momentum. If the trajectory deviated from purely gravitational prediction after perihelion, that deviation could signal either internal outgassing or active control. By the final week of October, amateur astronomers had no view left. The sun swallowed the object's position completely. Instruments on Earth-based solar telescopes searched for faint traces in coronagraph data. The same technique used to watch comets graze the Sunday, nothing conclusive appeared. Some images hinted at a small brightening, others at an unexplained shadow near the solar limb, but none could be verified. At ESA's control center in Darmstadt, engineers monitored JUICE's compressed telemetry packets. On October 30th, a burst of data arrived higher than normal bitrate, containing spectral readings still under analysis. Unofficially, one technician reported that the signal profile changed shape midway through the recording, as if the light source had briefly shifted or flared. The data were forwarded to joint teams at NASA and ESA for evaluation, where they disappeared into standard review protocols. Outside official channels, speculation ran wild. Some claimed to detect faint radio echoes in amateur recordings the following day. Others insisted the object had fragmented, pointing to subtle drops in solar wind density. Without confirmed images, every interpretation was guesswork. Perihelion came and went in silence. The world waited for reappearance, expected in early December, when 3I Atlas would emerge from behind the sunday. Between those dates lay uncertainty 39 days without observation, the longest blind spot of the mission. For astronomers, it was a test of patience. For everyone else watching, it was the pause before an answer that could redefine the boundary between natural and engineered worlds. As the sun swallowed 3I Atlas from view, every model, theory, and belief about the object condensed into two competing scenarios. Astronomers called them simply Outcome 1 and Outcome 2. Both fit the known data, yet they led to entirely different interpretations of reality. Outcome 1 was the conservative option, the natural explanation. In this view, 3I Atlas was an unusually large interstellar comet whose anomalies were the product of composition and chance. The nickel emission without iron, the reversed tail, the alignment with the ecliptic, all could be explained through rare but natural processes acting together. Perhaps the object's rotation caused jets of vapor to interact in complex ways, creating apparent symmetry. Maybe its orbit, while improbable, was the result of gravitational scattering from distant stars. The missing data, the silence from NASA, the timing of the government shutdown, these were political accidents, not deliberate control. If Outcome 1 held true, perihelion would strip away the mystery. The object would flare in sunlight, lose mass, and drift away toward interstellar space, leaving behind a trail of ordinary dust. Outcome 2 was the disruptive alternative. It began with the same observations but accepted that coincidences stack too neatly to be random. The mass stability, the polarized reflections, the repeating 12-second signal, the magnetic responses to observation each could represent design. If 3I Atlas was built rather than born, perihelion might not destroy it. It could trigger something else entirely. Heating might activate dormant mechanisms, release probes, or alter trajectory intentionally. This hypothesis required no conspiracy, only acknowledgement that the universe might contain self-directing machines older than our civilization. In late October, research groups quietly placed bets on which outcome would prevail. Some calculated probabilities. Others wrote private notes they never intended to publish. The split hovered near even. What unsettled everyone was that both scenarios relied on measurable, verifiable predictions. In Outcome 1, the object's trajectory after perihelion would deviate from gravity due to gas ejection, showing a detectable push away from the sunday. In Outcome 2, the motion would remain perfectly smooth, as if compensating for heat effects through internal control. Either way, the change or lack of change would be visible when it reappeared in December. Meanwhile, chatter leaked from inside mission teams. Technicians working with solar orbiter data hinted that new frames showed a faint persistence of brightness, suggesting survival. A brief internal report circulated describing post-perihelion reflectivity consistent with metallic composition. The language was cautious but pointed. If the nucleus had survived intact, it meant it did not behave like ice. The first scenario weakened, the second grew stronger. To calm public speculation, NASA's outreach office issued a statement reminding audiences that interpretation awaits complete data correlation. It was a careful way of saying nothing while acknowledging expectation. Still, journalists noticed that the agency began referring to 3I Atlas in the present tense. The object is now expected to re-emerge rather than the past. That subtle shift hinted at confidence that it had not disintegrated. Inside online communities, debate turned philosophical. If outcome 2 proved true, the implications reached beyond astronomy. It would mean the presence of artificial intelligence at a cosmic scale technology capable of surviving interstellar flight for centuries. If outcome 1 held, it would still rewrite comet science, forcing new models of magnetism, composition, and orbital evolution. In both cases, the discovery redefined what humanity knew about motion and matter between stars. As the days passed, and no clear word arrived from official channels, anticipation hardened into tension. Amateur astronomers prepared to resume sky, watching the moment 3I Atlas cleared the sun's glare. The date of expected reappearance was marked on calendars worldwide. Forums renamed it The Verdict. The 2 possible outcomes framed every conversation, every headline, every late-night discussion between scientists and journalists. No third explanation remained credible. Either nature had surprised us again, or we had finally encountered something that did not belong to it. The countdown to December was no longer just about an object's return. It was about which version of reality the universe would allow to continue. In the first week of December 2025, telescopes across the world began searching the dawn sky, where 3I Atlas was predicted to reappear. For 39 days, the object had hidden behind the sun, unreachable to observation and imagination alike. Scientists expected to see either a dispersed debris cloud marking its destruction, or a dim, fading remnant moving along its projected outbound path. What they found instead was neither. On December 6th, the Pan-STARRS Observatory in Hawaii registered a moving point of light matching the expected coordinates, but with one striking difference: its brightness was unchanged. No comet had ever emerged from perihelion without either dimming or disintegrating. 3I Atlas appeared exactly as it had before, still pulsing in that faint 12-second rhythm first seen months earlier. The data was checked twice, then 3 times. The object had survived the heat of the sun intact. Within 24 hours, confirmations arrived from observatories in Spain, Chile, and South Africa. The reappearance was real. The object's position matched gravitational predictions to within a fraction of a degree, yet something subtle was off. The velocity had shifted by a few meters per second, tiny but measurable. For natural comets, non-gravitational acceleration always points away from the sun, the result of gas venting. This time, the acceleration vector was perpendicular to that direction, as if the object had applied a sideward correction. ESA released a preliminary statement calling the deviation within normal uncertainties, but mission engineers privately described it as a controlled change of course. It was too precise, too orthogonal to solar pressure, to be random. The simplest explanation was thrust deliberate or mechanical. The revelation leaked through informal networks within days, reigniting public fascination that had cooled during the blackout. Spectral data brought another surprise. The nickel emission lines that had dominated pre-perihelion observations were gone. In their place appeared a broad infrared signature, consistent with heated ceramic or composite material. The composition of the surface had changed. Some speculated that an outer layer had vaporized, revealing something denser and more uniform underneath. The idea of a thermal shield, once dismissed as science fiction, resurfaced in research discussions. Radar stations attempted to probe the returning object, but the reflections came back distorted. Instead of the diffuse echoes typical of irregular rock, they produced narrow peaks that fluctuated on a 12-second cycle, matching the optical pulse. Each peak suggested a smooth, rotating facet. The data hinted at geometry planes and edges hidden beneath the earlier cometary glow. On December 11th, the Deep Space Network briefly lost lock on the signal it was using to track the object's position. When contact resumed, the tracking frequency had shifted upward by a small but precise increment. The kind of Doppler drift that could only occur if the source of reflection had changed its transmission characteristics. No official explanation followed. Public interest surged again. News outlets labeled it the Verdict Week, running headlines like "Still Intact, Still Silent," and "The Object That Refuses to Die." SETI facilities resumed, listening at 1,420 MHz, but no hydrogen-line signals appeared. The radio silence was absolute. The only rhythm that remained was the faint, regular glint visible in optical data, a silent clock marking 12 seconds over and over again. At an international press briefing, NASA and ESA scientists presented their combined analysis. The object, they confirmed, had survived perihelion with negligible mass loss, displayed a minor trajectory deviation, and emitted no detectable natural. By mid-December 2025, the data was in. 3. I-Atlas had survived its passage by the Sun, altered course ever so slightly, and continued outward along a clean, silent trajectory toward the edge of the solar system. The questions that had defined the previous 6 months remained unresolved. No scientist could explain the combination of density, geometry, alignment, and composure that made the object behave as if guided. Every hypothesis had failed to close the gap between natural and artificial. The only certainty was that something extraordinary had crossed our system and left it changed. In public statements, agencies kept to neutral language. NASA's December bulletin referred to the object known as 3I Atlas rather than Comet 3I Atlas, quietly dropping the classification. ESA described it as a non-typical interstellar body of interest. These small edits told the story better than any headline. The language of assumption had disappeared. The agencies weren't claiming it was artificial, but they were no longer sure it wasn't. Astronomers continued tracking it as it receded beyond Jupiter's orbit. Each night, the light curve remained steady. There was no fragmentation, no fading, no rotation drift. The 12-second modulation persisted with atomic precision, measured by synchronized observatories across the globe. It did not slow or accelerate. It simply continued, unbroken, like a metronome counting through space. Some scientists began using it as a timing reference for calibration, an unintended role for an object that might already have been built to measure something far more important. At the same time, background cosmic radiation readings showed a faint rhythmic suppression around the object's position. The effect was microscopic, barely above instrument noise, but its pattern mirrored the same 12-second interval. Statistically, it could be coincidence. Emotionally, it did not feel like one. The phenomenon led to quiet speculation that 3I Atlas might interact not only with light and magnetism but with the very medium of space, modulating the vacuum fields themselves. No one wrote that in papers, but everyone talked about it in hallways. On December 20th, a team at the University of Kyoto published an analysis projecting the future trajectory of 3I Atlas. According to their model, the object would exit the solar system at a slightly altered inclination, not the expected continuation of its inbound path. Instead of returning to interstellar darkness, it was steering toward a region near the heliospheric boundary, an area where the solar wind meets the interstellar medium. That shift, subtle yet deliberate, would position it perfectly to study the structure of that boundary. For some, that explained everything. The object wasn't here to communicate or to threaten. It came to measure. Governments showed no sign of reclassifying the event. Official reports emphasized the scientific opportunity rather than the philosophical implications. But private agencies, defense analysts, and independent astronomers all noticed the same pattern: unprecedented coordination between NASA, ESA, and private observatories to continue long-term tracking. The project was given a quiet internal name: Continuing Watch. It wasn't an investigation anymore. It was surveillance. By Christmas week, 3I Atlas had faded beyond the reach of most optical telescopes. Only deep space radar could still trace its echo. The signal was faint, but consistent, repeating every 12 seconds with mechanical precision. On the last night of tracking before the holiday, an engineer at Goldstone noticed something odd. The phase of the signal shifted slightly, as if the pulse had acknowledged its listener. It might have been an artifact, an error in calibration. No one could confirm it. The report stayed unpublished, another footnote in a growing archive of mysteries. The object kept moving outward, towards silence. Humanity, for all its instruments and debates, could only watch. Theories would rise and fall, data would refine, arguments would stretch across decades, but the truth had already slipped beyond reach. In a universe that reveals itself in fragments, perhaps 3i Atlas was never meant to answer our questions, only to remind us how little we truly observe. Somewhere beyond Jupiter's cold shadow, the light of a small perfect cylinder still flickered every 12 seconds. It neither called nor hid. It simply existed. And the universe, vast and unbothered, continued to watch quietly. If you've stayed with me to the end, you've just witnessed one of the strangest chapters in modern astronomy. 3i Atlas came, broke our models, and left without a sound. Like and subscribe to stay updated as new data comes in, and tell me in the comments where you're watching from and what time it is there right now. The universe doesn't rush to explain itself. It just keeps moving. And somewhere out there, so does 3i Atlas.